Hello, my name is Michael Jones, and today we are going to be analyzing images worth 16 by 16 words, transformers for image recognition. And this is quiz 1 for computer vision. So, as a background, CNNs have dominated the field of computer vision. The inductive biases allow them to be efficient with small data sets. These include locality. The convolutions look at local neighborhoods. The filters look at local neighborhoods. And translation equivariance. An image shifted side to side, the filter still goes through the whole image. So it doesn't really make a difference, but that's just for shifts. We'll talk about that later. Uh, However, the disadvantages, it struggles to capture long-range dependencies, and it struggles with scaling. So we added on to CNN and attention hybrids, and this is better for capturing long-range dependency, and it's still efficient with small and medium data sets. The disadvantage, though, it's computationally inefficient. You are having two different architectures, and both of them have their different costs. And with two different architectures, it increases that architecture complexity. So the motivation behind this paper is to help solve some of the challenges of computer vision. High dimensionality causes computational burden. So the high dimensionality of the images are 2D. So if you have a 200 by 200 pixels, that's a 40,000 something pixels individual compared to a sentence with just 20 or 50 words tokens. And in pictures, global features tend to be more important than in text. Also, there's problems with the variability that you don't have in text. Some objects could be at different scales, could be rotations, there could be skews, uh, uh, contrast differences, and also general data scarcity. There's billions and billions of freely available text, words, comments. Um, Images are more expensive to compile a very large data set. So the motivation is, can transformers help us solve any of these challenges of computer vision? So why use transformers? Transformers have dominated the field of NLP with architectures such as BERT and GPT. Uh, so what would happen if we use them in computer vision? Transformers, they're good for capturing long-range dependencies. Uh, they scale better with the size of the data set, and they're more easily interpreted than CNNs. Attention maps uh, show which region influences uh, other regions better. So we'll go into the methods. Transformers for computer vision use patches as tokens. The image is split into patches. The number of patches is given by, you see there, the height and the width of the image divided by the dimension of the patches, 16 by 16 in our case here. These patches are now used as our tokens, like words were in NLP. And from there, we flatten and embed them. We flatten them into a single vector. And the problem here is possibly our vector and the model's dimension don't have the same dimension. So we apply matrix multiplication and we map these to an embedding vector so they match. Another different thing is CLS tokens. We add these special tokens to the beginning of each patch sequence, And what these are, these aggregate information from all the patches via the attention. And of course, like the others, we have to add positional encoding because we need to keep track of the patch order. So as far as the transformer encoding, we have a multi-head self-attention. Basically, each token, each patch sees how strongly they relate to the other patches, every other patch. It's computed as a weighted sum of all embeddings given by our equation there. You got the attention score, the query times the key transpose, how well they relate, and then it's scaled down to help stability there by the dimension of the key, and then it's run through a softmax activate or function to get it into probabilities. And the good thing is these multi-heads could be run in parallel, and each head could focus on a different pattern, say edges, color, things like that. And after that, there's a feed forward MLP. This introduces nonlinearity on each token individually through 2 layers with a GELU activation function. We have, like the other, we talked about residual and layer normalization. It's prevents gradient explosion or vanishing and helps with stability, training stability. And then finally, our special CLS, we have CLS embedding that is fed into our MLP classifier. And it the good thing about that, all the aggregate information from all the patches is in that one embedding instead of feeding every embedding into that classifier. So now we'll start with the results. As far as performance results, the metrics here of our chart are task accuracy after pre-training, and our flops are floating point operations. Some good takeaways here. The vision transformers perform better than CNNs when pre-trained on large data sets. However, the VITs with the highest accuracy are computationally expensive. If we look at our chart, the VITs H14 there, we see it's 4,262 exaflops, and that is very large, larger than basically any comparable one. So the hybrid offers a good middle ground between accuracy and cost. And the good thing, transformers and hybrids transfer well to smaller data sets. From the trained on the big data set, they transfer well on the smaller data sets like pets and flowers and specific classes. They also scale well with model size and data size. So, and this is the results of scaling. Our chart here, the x-axis is the number of samples from JFT the model was trained on, and the y-axis here is the percentage of 5 test images per class where the top prediction of the model equals the ground truth. It's called linear 5-shot ImageNet top 1%, and that's just a long, confusing name. The main takeaways here is ResNet, our hybrid model, performs much better on smaller training sets, and that's the CNN in there helps that out. But as the number of images, the trained images grow, the large model VIT eventually surpasses it. So conclusions and insights here. In the paper, we saw that A plain transformer with patch embeddings using patches other tokens is comparable to the current dominant model, hybrid or CNN, given enough pre-training data. But the inductive biases of the CNNs help it on smaller data sets where transformers struggle. The VIT scales well with model and data size, and the VIT gives excellent transfer performance. Thank you so much.